So now the question is, how do implementation details affect how fast this algorithm operates? So some of the answers to this question are straightforward. Right, so the first question we can ask is, how many deletes do we have to do? Right, and so we can kind of come up with a representation of, as a function of how we represent our heap, here's how many deletes have to happen. And so let's take a look at this, right? Where the only place the delete min operation ever happens is here. And that happens on the inside of a for loop that goes from, that ticks v times. So there are exactly v delete mins. Right, so that happens exactly v times. And so now what we can do is we can say, well, regardless of what happens afterwards, now we can actually write down the total effort that is expended on delete mins. Okay, so let's do this. So what do we have up here? Well, we've got a characterization of the algorithmic cost of these. So I'm going to copy this down below. So I've copied this down below. Let me shrink it. Okay, so we know that no matter how the graph is represented, we know that there are going to be exactly this many delete mins. And so now we know something about the total effort that's expended on delete mins. So we know that if we use, so let's do this. Let's do total delete, running out of space there. So we'll do total delete effort. Well, if we use a min heap, there's v delete mins, and each one takes log v times. So it's v log v. Okay. If it's an unordered array, we know that there's v deletes, and each one takes v time, so it's going to be v squared. All right. So now let's think about the update piece. So we know that the update, if we're using an unordered array, we know that the update is basically free. Right? It doesn't take up an interesting amount of time. All right. But if we have a min heap representation, the update does take some time. Right? It's not totally free. On a very, very, very large graph, it'll take some time to do this update operation. So let's think about how the way we represent our graph can impact the efficiency of this algorithm. And so let me just remind you of the two different ways we could represent our graph. Right? We could represent our graph as adjacency lists. And so recall how adjacency lists work. We write down a list or an array of some kind for each, some linear data structure for each vertex. So we've got v1, and then here we've got a list of the vertices that v1 is connected to. Right? So this is I'll just write neighbors of v1. There we go. And then v2, and we have the neighbors of v2, and so on. Okay. So the adjacency lists, in some sense, represents edges explicitly. Right? If I ask for a node, if I ask for v2, then the list here is essentially a list of the edges connected to v2. So we don't waste a bunch of space describing edges that don't exist. We only describe edges that do exist. So the alternative, and for this problem, the alternative is called something slightly different. It's called a weight matrix. The alternative is to encode the whole thing as a matrix. And so a weight matrix looks like this. Right? It has, I'll just draw it as a grid. So it has it has exactly v rows and exactly v columns. And what does a cell mean? So let's call this cell ij. This cell right here contains the weight of the edge that connects node I to node j. Right? So this is the weight of edge ij. All right, so let's think about where the representation of the graph comes into our algorithm. And so to do this, let's go back up to our pseudocode. All right, so our pseudocode has this loop where it says, each time this loop ticks, we add a new graph to our tree, or a new node to our tree. right? So there's exactly v ticks here. There's nothing intrinsic about the graph representation here, right? In either graph representation, we have essentially a list of nodes. Either it's the rows of our matrix or it's the list of adjacency lists. So this isn't dependent on the graph. But then notice that what this loop does is it says, this for loop, for each node that we add to the tree, it says, let's go find the neighbors of that node. So there's a hidden search through our graph representation in this line of code. Okay? So this line of code is find the neighbors. Find U star's neighbors. And so the question is, how do you find the neighbors of a node in a graph representation? Well, if we are using adjacency lists, you just say, well, let's suppose we're asking the question about V2. Well, there's the list of its neighbors right there. We're done, right? The list of its neighbors is a compact representation of the neighbors. So all you have to do is walk down that list and you're done. If, on the other hand, we're using a weight matrix, then we have to ask, what is the list of the neighbors here? Well, if we're asking about V2, right, this is the row corresponding to V2. And what are V2's neighbors, or what are the nodes that have an edge from V2 to that node? Well, it's encoded by this row. And so to find the neighbors, right, and some of the weights here are infinite, which means that there's no edge, and some of the weights are finite, which means that there is an edge. And so if you want to understand who the neighbors are of V2, you have to walk down that entire row. Right, so the length of this for loop right here is a function of the graph representation. Okay, it can be short if we're using adjacency lists, or it can be order v long if we're using a weight matrix. So what we can say here is if we are using a weight matrix, this is v steps. Okay. Otherwise, it's less. Okay. And so here's what I'm going to do. I'm going to put in another row here. I'm going to scoot this down just a little bit. And I'm going to give you a hint. I'm going to say whenever we're using a min heap to represent our priority queue, we want to use adjacency lists for our matrix, for our graph. Okay, so I'm going to put here adjacency list. And I'm going to say whenever we're using an unordered array, we can use a weight matrix. So here we'll use a weight matrix. So let's focus on the weight matrix first, because that's what we've just been talking about. So if we're using a weight matrix, we want to add another row here that says the second for loop. Second for loop is where the updates occur. So I could say this is where the updates occur. If I'm in the second column, so I have a weight matrix and an unordered array for my priority queue. The question is, how much effort is expended on this second for loop? And let's see. Well, how many times does the for loop tick? Well, this second for loop ticks exactly v times. Right? So there's v calls to this for loop. And then how long is the for loop? Well, if we're using a weight matrix, it's order v. Okay? So we have a total effort here of, again, v squared. Right? Nothing new here. So what it, and then there, some of those ticks of the for loop will involve an update, but the update is basically free. So we don't care about that very much. So now let's think about what happens if we've represented our graph as an adjacency list, and we're going to use a min heap for our priority queue. What's going to happen? Well, the nice thing about the min heap is that updates don't cost too much, but we want to make sure that we don't have an extra factor of log v multiplied onto this v squared. We want to see if we can keep this down. So we'll use adjacency lists that reduce the length of this for loop, right? Reduce the number of ticks in this for loop every time it runs. And so let's think about, how many updates occur when this algorithm runs. So the core question now is for here is how many total updates? total updates. And to think about this, it's useful to draw a little example graph. So suppose I've got a graph that looks like this. And here's my root, right? So there's S. And it's just, suppose it's something like this. So what happens when I add S to my tree? Well, I have to go search the neighbors of S to make sure that, to update their weights. And so let's keep track of which edges I've looked at. So I've looked at this edge, and this edge. Okay, so then in the next step, I'm going to add another neighbor to my tree, right? So suppose I add this, and the question now is which edges get added, which edges get looked at, right? Which edges could have an update associated with them. Notice that every time I look at an edge, it could result in an update. Okay, so the number of updates will be less than or equal to the number of times I look at an edge. So when I add this upper node here to the tree, I look at its neighbors at the edges, or I look at all of its neighbors, which means that I look at each of the edges leaving it, and each of those could result in an update. And then, so then those are my adjacent nodes. So now let's see what happens if I add, say, this one to my tree. Well, then I go look at its neighbors, right? So, and each one could result in an update. So, that's a possible update. That's a possible update. And now let's say I add this one to the tree. Well, now I go look at its neighbors, and there aren't any neighbors. It has no neighbors that aren't already in the tree, right? So that means that there are no more updates. Okay, so this edge could have had one update, but not two updates. This edge could have had one update, but not two updates. One but not two, and so on. Okay, so if we've represented our graph as an adjacency list with the adjacency list structure, then what we have is this guarantee that second for loop is never longer than it has to be. It only ever looks at the neighbors of the node. And we have a guarantee that we never have to update more than once per edge. Okay, so the total number of updates, if we're using adjacency lists, is E, right? So here's the total number of updates. So what I'll do here is I'll write, this is max number of updates. We never have to update more than once per edge. We know we can find the edges efficiently. We don't have to search through an entire row of the weight matrix. And how long does each update take? Well, log v. So now we're almost done, right? So if we're using, and I'll encode this in blue, this representation. So our priority queue is a min heap, and our graph is represented as an adjacency list. Then I'll go here and I'll say here's the total, right? So it's v log v, v log v plus e log v. And so this, I can factor out the log v, and I get log v times the number of vertices plus the number of edges. Well, what do I know about the relationship between the number of vertices and the number of edges? Well, I know that the number of edges can't be less than the number of vertices. Okay, so this is always going to be less than or equal to E log V. All right, so each vertex has an edge, right? So the number of edges is essentially bounded by the number of vertices, so I get this. So there's my complexity if I've used this representation. If my representation is adjacency list for the graph and min heap for the priority queue. So now I'll switch colors and say, what if I've used a weight matrix? What if I've used a weight matrix for my graph and an unordered array for my priority queue? Well, then it's just this. It's just v squared plus v squared, which is v squared. Which is just, big theta v squared. Okay. So you look at these and you say which one's better, and it turns out it depends, right? And so this is going to be something you'll look at on your homework, is you'll try to understand, as a function of what the graph is like, which one of these representations causes Dijkstra's algorithm to be faster. And you'll take a good deep dive into that.